Okay, good morning. That was really sad. Good morning. Okay, that's acceptable. So we got this exam coming up a week from tomorrow. It's September 29, Thursday, 6:30 to 7:30 p.m. Everybody will be in the Elliott Hall of Music. So if you are in my lecture, we will be on the main floor. And where you sit depends on who your TA is. So what I want you to do after class today is go to the course page, look up the exam 1, this thing right here, and it'll show you this thing. Now it's kind of hard to see on the projector here, but you could zoom in a lot more when you download this thing and get a better look. Okay, so find out where your TA seating block is. For example, if you are in Jeff Zielinski's class, you will be in this section, in the back. Okay? Also make a note of which aisle you should go in. Again, as an example, if you're in Jeff Zielinski's class, all the way in the back here, you should go in either through aisle 4 or aisle 3, aisle 4. It just makes it easy for you to find your seat. If you're in Anna Rose Wolf's class, please go in through aisle 5 or 6. Does that make sense? And your TA is also supposed to assign a seat for you. And some of them might have done that yesterday when you went to recitation. If they haven't done so, then next time you go to recitation, they will tell you where your seat is. It's just to help you get into a location very quickly. If you know exactly where you should be going, just head directly there. It makes things go smoother. And on the map online here, zoom all the way in, and you should be able to find out where you're supposed to sit. So if you're in Anna Rose Wolf's class, and she tells you you should be in row P, seat 106, that's where it is. Yep? Okay, so make sure you take a look at this. And by show of hands, how many of you got a seat assignment from your TA yesterday? Very good. And then, like I said, if you have not gotten it, next time you go to recitation, you should be getting that. Also, on the exam Scantron, you will need to put in your section number. It's a 4-digit number. And on the second projector here, I have the section number for you. The section number makes sure your score goes to the right place. If you have the wrong section number or no section number, your score could be not where it should be, and that wouldn't make you very happy. Okay? So that's to make sure that the score goes to the right place. As an example, if you're in Anna Rose Wolf's class, and your recitation is 8:30 a.m., you should put down 0608 as your section number. If you're in Dongming Xie's class, he's actually filling in for Jacob Bond for the first few weeks. If you're in his class at 2:30 recitation, you should put in 0610 as your section number. Does that make sense? Yeah? So make sure you know where you're supposed to go and know the section number. We will remind you at the exam, but there's going to be a lot of things going on at the exam. So, we don't want to make you feel too rushed or anything. The more you know by the time you get there, the better. All right. And I'll talk more about the exam, including which all the exams you should be looking at either on Friday, or if I have information to share, I'll send them by email before Friday. Sounds good? Okay, good. All right. Today we're going to look at section. We'll finish 14.4. We started 14.4 last time. We'll finish that today. We're going to go through another example of linear approximation. So last time you saw one application of linear approximation using a tangent plane when we interpolated entries in a table. Today we'll do something using the same principle, but a slightly different application. And this is an application that analyzes the error. Let's call this error analysis. So what happens here, when we're measuring something with a ruler or with a tape measure, there's always some kind of error. Your ruler is never perfectly precise. So there's always some kind of error built in. We're going to find out when we make an error in the measurement, what does that do when, to the, say, the volume of an object. Here, let's use an example. We have a cylindrical can. And it's designed to have a radius of 1 inch and a height of 5 inches. But there is an error in the measurement of at most 0.1 inches in each of those in the radius and the height. We want to find out if I make a seemingly small error in the measurement in the radius and the height, how does that affect the calculated volume? In other words, a 0.1 inch error in the measurement translates to how big of an error in the calculated volume. Okay, so think about this. If you're designing, let's say, the fuel tank of an airplane, and you know this airplane is supposed to carry this amount of fuel. Now, if you can't measure the dimensions of that tank very carefully, very precisely, there will be an error in the volume of that tank. And that's going to affect the distance that airplane can travel and the amount of passengers, cargo, whatever. So it's a very, very serious problem when there's an error in the measurement. Okay, so let's see. Here's our can. The radius and the height. What's the volume of this cylinder? Yes, the base area times the height, right? Pi r squared h. This is one of those basic shapes that you should know. More exotic shapes, we don't expect you to memorize, but the basic stuff like a cube, like a box, like a cylindrical can, that's the kind of thing we expect you to know. Notice this is a function of two variables, r and h, right? So what's going on here? We think r is 1. But there's an error of at most 0.1. So in reality, it's somewhere between 0.9 and 1.1. Right? We measure 1, we think it's a 1, but there's a measurement error in that ruler. with a 0.1 maximum error. So it's somewhere between 0.9 and 1.1. It could be 1.02, it could be 0.93, but it's somewhere between the two. But our best guess is 1. Same thing here. H is 5, but in reality, it's really somewhere between 4.9 and 5.1. So you can see that we're not so sure about R, we're not so sure about H. So when we calculate the volume, we can't be sure about the volume. And we want to analyze how big is that uncertainty in the volume is. Now I'm going to cast this in terms of a linear approximation problem. This is equivalent to this problem that we did last time. If we change R and H by small amounts, how does V change? Okay, we're going to find out with small changes in these two variables, how does that affect the variable V, which is based on R and H. So here we're going to use the idea of differentials. Because remember, differential gives you approximated change in the variable of the function based on the change of the two variables, or however many variables. So here's the volume formula. The differential in the volume, dV, remember this is the partial derivative with respect to R times dr plus partial derivative with respect to H times dH. Remember that? Yes? Okay. So let's see what this turns out to be. Partial V, partial R, looking at this. Now we treat H as a constant, right? So this is 2 pi R H. dr. And then partial derivative of V with respect to H. This time H is a variable, R is a constant. So we have big constant times H. Derivative is simply whatever that big constant is. Okay? Remember these D's we did last time, these are the uncertainties, the errors. Which really means the change in the variables. And here in this context, those will represent the error. And these plain R, H, and these things, these three variables without D attached to them, these are what we think they are. Which is our measurement. Right? Our best measurement is that R is equal to something, H is equal to something, and here are the errors. Just like what we did last time, we used these points to build a tangent line approximation. And then we move by a small amount on that tangent line. And if we don't change too much, we should be near the surface. So it's exactly the same idea. Okay, now let's toss in the numbers we know. 2 pi RH. We think R is 1, that's what we measured. We think H is 5, we measured that. dr, that's the error we made. It's 0.1. Is that me doing that? I'm not doing anything. Okay, nothing. See, there goes my mic. All right. Nothing looks wrong, so let's keep going. Okay, and then here we have pi. We think R is 1, right? That's our best measurement. And then dH, that's the error we made in the measurement of H, which is also 0.1. So this turns out to be 1.1 pi, and the units would be cubic inches. Okay? Now let's look at how big this really is. If R is equal to 1 and H is equal to 5, V is pi R squared H is equal to 5 pi. So this 5 pi is what we think the volume is. If our measurements are perfect, then the volume is 5 pi cubic inches. This is the error that we potentially need to account for. So this is the error in volume calculation due to errors in R and H. So make a note of this. We only made a 0.1 inch error in each of these two variables. Those are not very big, right? Those are very pretty small things. But in the end, look how big the error turned out to be in terms of the volume. And it's actually, this is like 20%. 20% of what we think it really is. So the volume, in reality, is 5 plus or minus 1.1 pi. So that's 3.9 pi or 6.1 pi. That's a very, very large range. If you're designing this for an airplane and you need to carry passengers for 1,000 miles, and you can't be certain about how big that tank really is, that's not a good thing to do. That's very, very bad. Because if you're underestimating, then you're in trouble. If you're overestimating, then fine. Right? Well, no. That's right. If you're carrying enough and it really turns out to be this, then you're fine. But suppose you're not carrying enough fuel, then you're in trouble. Well, your passengers are in trouble. Okay? So this happens a lot in a lot of engineering and scientific applications. You make seemingly small errors in the beginning, and the errors will propagate into something that can be very, very large. And errors always propagate. They never get smaller. They may stay the same if you're lucky, but they always get bigger whenever you work with uncertainty in variables. So how do we improve this if we want this to be smaller? What's the source of this uncertainty? In the measurements, right? So measure things better with a better instrument, maybe a laser or something. If you can shrink the 0.1 here, then this will shrink. Does that make sense? Yeah? Good. All right. Now today we're going to start a new section here. This is 14.5. We're going to look at the chain rule when we have functions of many variables. Once again, let's revisit the one variable case. You remember that if y is some function of x and x is some function of t, then the rate of change of y with respect to t, because y really is a function of t now. It has an intermediate variable of x and then a final deep independent variable of t. So how does this go? Remember what the formula for that is? The chain rule? Right. So the rate of change of y with respect to its own variable, dy dx, times how that intermediate variable is changing with respect to the true independent variable. Think of the dependency tree here. Y is at the top. Y depends on x, and x finally depends on t. So y really is affected by t. But t will first change x, and x then changes y. So we need to step down each time by using a derivative. Okay? So going down from y to x, the rate of change is given by dy dx. Going from x to t, the rate of change is dx dt. And you put this together, you chain them together, then finally you can figure out how y is affected by t. Okay, now let's look at what happens when we have more variables. The first thing what's going to happen is that the tree gets more complicated. And you'll see how we deal with that. Let's say that z is equal to x squared plus y squared. But each of these variables, x and y, really is a function of another variable. Let's call that t again. Okay, so z depends on x and x and y in turn depend on t. So really, z is a function of t at the very, very end. Ultimately, z is a function of t. We want to find, if I change t, how is z affected? Same idea here. If I change this variable here, how is y affected? Let's look at a variable tree. Now we have branches now. Z is at the very top, right? Z is dependent on everything else. And z is going to depend on two things, on x and y. Two intermediate variables. X and y both depend on t. Okay, so now we got this tree that branches and then eventually merges into t. Now you can see, obviously, if you tweak t a little bit, x and y will change, and then z will finally change in response to those two. When you write the chain rule equation here, you have to look at the two branches separately. So first we need to account for how z is changed by x and then changed by t. the rate of change of z with respect to t, first the left branch, the green branch here, when you have a split, you want to use partial derivative. So the left branch here, we have a split here. First, we need to capture how z is changed by just x. So that's a partial derivative of z with respect to x. This will capture how x alone affects z. Then we need to capture how x is affected by t. But x only depends on one variable. There's no split here. So that's a regular derivative. So we got funny d and regular d's mixed together. Funny looking d is when there's a branch. When there's no branching, you use a regular derivative. So that accounts for how z is changed by x and then changed by t. Now let's look at the other side. This other branch here. We do the same thing. Z has a split. So to capture how z is changed by y, we do a partial derivative with respect to y. And once we get to y, y only depends on one variable, t. So it's a regular derivative. Does that make sense? Yes? Good? All right, then let's figure out these parts. Partial derivative of z with respect to x, that's just 2x. Partial derivative of x with respect to t is negative sine t. Partial derivative of z with respect to y is 2y. And partial of y with respect to t is cosine of t. All right, so there we go. That's a partial derivative of this function with respect to t. So remember, we got a bunch of different d's. This is the funny d, regular d, Any question on this example? Are we clear on when to use which d based on the tree? All right, then let's make the tree more complicated this time. Z is inverse tangent of x minus y, and x and y depend on two variables, s and t. All right? Okay, let's draw our tree. Z is at the very top. Z is the result of all these other things. Z is at the top. Look at the equation here. Z is immediately affected by x and y. We have a branch. Now let's look at how x and y are affected by other things. X and y are both affected by two more variables. So there's another split here, 2s, 2t, 2s, and then goes to t. So looking at this tree here, z is ultimately a function of s and t. Not directly, because there's an intermediate x and y involved. Whenever s and t are changed, x and y are changed. When x and y are changed, z is changed. There's a chain reaction going from the bottom of the tree to the top of the tree. So z is really changed by s and by t. Let's find out how that happens. How these two are, what they look like. Notice I used the funny looking d here because z is really a function of s and t. If I want to know how s is changing z, then I have to momentarily hold t constant. So we're talking about a partial derivative. Same thing here. If I want to know how z is changed by t, I have to momentarily hold s constant. So that's a partial derivative. In the last example, z ultimately only depends on t. That's a one variable function. So that's the regular d. There's no other variable to get involved. All right, so let's try this one first. Partial z, partial s. Z is affected by s in two ways. One is the leftmost branch by the route of x, right? And then a second branch this way. I'll use green because I use green for that. So let's look at the first branch here, just the diagonal down. Z to x. Z has a split. So it's partial z, partial with respect to x. Right? Now we're at the second level. Now going down another level. First of all, which d do we use? Funny d or real d? Real d, regular d. Going from here down to s. Regular or funny? Funny d. So partial x, partial s. Right? This captures the first branch, the first route. Now we need a second route here. Funny d z, funny d y, right? And then y to s, another partial derivative. So that's our route number 2. Does it make sense up to this point? Nod your head if yes, so I can see. Good, wonderful. All right, now let's fill in the details. Who remembers the derivative of an inverse tangent function? Let's do the simple one here. What's the derivative of inverse tangent of x? 1 over mumble. 1 over what? I hear 1 and then what? X squared, yes, plus or minus. If you said minus, you're wrong. It's plus. Okay, so this is the kind of thing we expect you to know too, okay? You don't use it very often, but something you should know. All right, so let's fill in the blanks here. Partial derivative of z with respect to x. So it's 1 over 1 plus x minus y, the quantity squared, right? Partial derivative of tangent of blah is 1 over 1 plus blah squared. And now you got to use the chain rule, derivative of x, and that's a 1. So this is really a multiplied by 1 here. This guy here is partial z, partial x. Then partial derivative of x with respect to s, 2s. Is that clear? Okay, what's the partial derivative of z with respect to y? Just this part. Good. Why is it negative? Very good. Right? The negative here, this is because of the coefficient of y. There's a chain rule. Here, this is the chain rule because x has a coefficient of 1, just a 1. Y has a coefficient of negative 1. This makes it a negative. Because y has minus sign. Okay, and then partial y, partial s, minus 2t, right? Simplify this, they have the same denominator. 1 plus x minus y, the quantity squared. We have 2s up here, minus 2t, so 2 times s plus t. Question about this? Good? Okay, very quickly, let's find the partial derivative of z with respect to t. How is z ultimately affected by t? Again, follow the tree. Z is affected by t in 2 ways. One by the route of x, the other one through the route of y, right? So to account for how t affects x and how x affects z, we do something exactly the same thing we just did. Partial z, partial x, and then partial x, partial t. And then the other route, partial derivative of z with respect to y, and then how y is then affected by t. Filling the details here. These 2 things we already have. How partial derivative of z with respect to x and y, we already have these 2 things from the last page. So I'm just going to copy that. And now partial derivative of x with respect to t is, what is it? What's partial x, partial t? 1, right? That should be easy. This we already have. It's negative 1 over that thing. So I put a minus sign here. What's the partial derivative of y with respect to t? (2s), negative 2s. simplify a little bit. 1, this thing downstairs, we have 1 upstairs minus 2s, so 1 plus 2s. I'm sorry? Oh, yes, it is. I copied it wrong. I'm sorry. Yeah, those should be positive. It's the same thing we used earlier, which I wrote them correctly. Good. Okay, so that's how z is affected by t. Questions? Nope? Okay, good. Along the same line, but this time suppose we don't know what these functions look like, but we have a table that gives us selected values. Let's say that if f is a differentiable function of x and y, and there's another function g and some other function g that depends on another 2 variables, r and s, is the same as f of these 2 things. Let's find the partial derivative of g with respect to r. Let's write it this way. G sub r at 1, 2. And here's the partial table we have. All right, so there are 2 functions that we don't know what they are, except from this table, we know a little bit about each of them at certain places. There's a function g that depends on r and s, and a function f that depends on x and y. We don't know what they look like, and right now, they have nothing to do with each other. Just some 2 differentiable arbitrary functions. But we know one thing is that this function for whatever r and s, whatever values of r and s, is equal to the function f when we plug in this. In other words, if we let x be this and let y be that, then when you feed x and y into this function, you will get whatever g tells you. There are 2 functions we don't know anything about except this relationship and this table right here. And you find out that actually we have enough information to figure out this question right here. All right, so this is what it really means. These 2 things are not equal in general, except that in this very specific configuration, when you make x equal to 2r minus s, y equal to s squared minus 4r. then these two functions will give you the same number back. All right, so how do we do this? Let me rewrite that thing I just wrote before we do more to it. If you want to find out how g is changed by r, you take the partial derivative with respect to r on the left and the partial derivative of whatever is on the right with respect to r. So this guy is really x, this guy is really y. On the right here, we have exactly the same thing we had going on here. We had an f at the very top that depends on everything else. And f will immediately depend on x and y. But then x and y will depend on s and r. Or r and s. R comes before s. So we'll do it that way. So that's what's really going on here. You have two functions you know nothing about except that this very specific way things are set up. When x is exactly equal to this, y is exactly equal to that, then they will be the same. So therefore, if they are the same, then the partial derivative will be the same. Okay, let's step down the tree on the right here. Take the derivative of f with respect to r. We need to go down this route first. So that's f x. xr, right? I'm using the subscript notation to denote partial derivative. Then the other route, fy, and then yr. So got to remember now, fx is a function of x and y. And xr is a function of r and s. Because x is a function of r and s, f is a function of x and y. So these two are still going to be the same. And left side is gr, g sub r, r comma s. Now we can find out what's going on at gr 1, 2. So we're talking about r is equal to 1, s is equal to 2. And what is x when r is 1 and s is 2? Look at the definition of x. 0, right? What about y? When r is equal to 1 and s is equal to 2, also 0? Okay. Here, xr, r and s, we know what r and s are, 1, 2. Same thing here. Fy, x is this, y is that. If r and s are these two, same thing, 0, 0. So let me write this down. This is x equal to 2r minus s. When r is equal to 1, s is equal to 2, x is equal to 0. Same idea for the y. Y r 1, 2. So now we look at tables, right? fx 0, 0, fx 0, 0 is 4. xr 1, 2. What is XR? How do we find XR? Definition of X is right here. So what's the partial of X with respect to R? 2, yeah? This is 2. What about YR? -4. See that? XR is the partial with respect to R of X, 2R minus S, and that's a 2. Same thing with that. So it turns out that these guys don't depend on R and S. That's okay. Okay, Fy00, 0, we look up on the table. Fy of 0, 0 is 8 times -4. So that's -32 plus 8, that's -24. And it turns out we only use 2 entries of that table. And that's fine. All right, that's it for today. See you Friday.